Yeah, thanks for joining this session of the virtual seminars in economic theory. We are very glad to see you all again. Today we have Liang from Northwestern, who is going to give a presentation on dynamically aggregating diverse information. We are pleased to have Annie's co-author Xiaosheng and two guest panelists, Konrad Mierendorff and Nicole Immorlica. The format of these seminars is as follows. We have 60-minute presentation with time for interim questions from the panelists, followed by 15-minute session for questions and discussion. Please, we request all attendees to keep your microphones muted during the talk. However, you can post comments and questions in the chat where Xiaosheng will answer, clarify questions in writing, and pass any important questions to many more important questions to Annie. There will be another opportunity to ask questions live in the Q&A session at the end. Just to inform you that the talk is recorded. Before I hand over to Annie, let me remind you that these seminars take place every Thursday, 4 p.m. UK time. Next week, we have Naguib Ali from Penn State presenting his paper Reselling Information with Hayal Chen-Jion and Eric Lillenham, with guest panelist Edward Talamas. As usual, you can find more information about the coming list of speakers on our website or by following us on Twitter. Without much further ado, thank you, Annie, and the screen is yours.
Awesome, thank you so much for having me. So as Malta's mentioned, this is joint work with Xiaosheng and Vasilis Syrgkanis. Thanks also to Konrad and Nicole for making time to be here today as panelists. So the paper is about dynamic acquisition of information. And specifically, we look at the question of how an agent should acquire information over time, when that agent has limited resources with which to acquire information, and moreover has to decide how to spread those limited resources across multiple different kinds of information. Right, to just give you a few concrete examples, suppose a mayor wants to learn the COVID incidence rate in a city and can allocate tests across different neighborhoods, but has a limited total number of tests. So how does he want to allocate those tests across the neighborhoods and across time? For a different example, consider a newsreader who wants to learn the unknown cost of a proposed policy. He can learn about that by reading articles from different news sources. How does he want to allocate his limited time across these different news sources? So what I'll show you today is a model of this dynamic information acquisition problem, where it turns out that the optimal information acquisition strategy can be exactly characterized, and moreover has a rather simple, easily describable structure. So I'll spend the first part of the talk just telling you what that characterization is and why it turns out to look like that. All right. Then the fact that the model turns out to be so tractable also means that it lends itself to applications. And in the paper, we use this characterization to derive new results in 3 settings motivated by particular economic questions. So I'll spend the second part of the talk explaining those applications and trying to highlight the different ways in which we think this characterization can be used. All right, so here's the model. We have k unknown attributes, theta 1 through theta k, and these unknowns are assumed to be jointly normal. In the COVID case, we might think of each attribute as being the COVID incidence rate in a specific neighborhood of the city in question. And in that example, as in many other applications, it's going to be important that the attributes are allowed to be correlated, where we might think that the incidence rate in neighborhoods that are, say, geographically closer or comprised of more similar demographics would have positively correlated incidence rates. Right. Now, the decision maker is going to have access to an information source about each of these unknown attributes, which formally we're modeling as a diffusion process. And I'll tell you more about how those diffusion processes are going to evolve in a moment. Right. Then, although there's k unknown attributes, there's going to be a single unidimensional payoff relevant state, which is a linear combination of these unknown attributes. In the COVID case, you can think about this payoff relevant state as being the aggregate COVID incidence rate in the city, weighting the different neighborhoods proportional to their the fraction of the city's population that is in that neighborhood. Okay, and throughout, we're going to assume that these payoff weights, alpha, are known to the decision maker. So all of the learning is going to be happening over the values of these attributes. All right. Now, attention allocation is the focus of this paper. And we're modeling that as follows. So time is continuous. And at every moment of continuous time, the decision maker is going to have a budget of resources or a budget of attention to allocate across learning about the different attributes. So formally, he's going to choose an attention vector summing to 1, right, where this choice of attention vector is going to determine how the diffusion processes evolve. So specifically, if we think about attribute I, the increment of the associated diffusion process at moment t is going to be given by this expression here. Right, so the drift is theta I, the attribute you're trying to learn, times beta it, which is the amount of attention you've allocated towards learning about attribute I at time t. Right, this part is an independent standard Brownian motion, and this part is a normalization factor. So what's important here is that devoting more attention towards any given source is going to lead the increment of that diffusion process to be more informative, right? You're improving the signal to noise ratio. And if you find discrete time models more sort of easier to think about, there is a parallel discrete time analog to our model. So in this discrete time analog, the decision maker would have in each discrete period a unit of precisions to allocate across k different Gaussian signals. Right, so each of these signals is a signal about the associated attribute theta I, and the precision on the error term is going to be determined by how you allocate attention. Right, so here, if we have these precisions summing to 1, then the two models are related in the sense that observing this diffusion process for 1 unit of time is going to be equivalent to observing 1 realization of this signal. Okay, if we further allow this to sum to not 1, but let's say some integer n, then you can actually think about this as some larger integer n. You can think about this literally as something like the COVID test case, where the decision maker has some number of tests to allocate across, say, different testing centers. Right, and then the error here would be 1 divided by the error variance would be 1 divided by the total number of tests allocated to that testing center.
Annie, I'm curious about your decision to restrict the attention to be linear in the amount of attention I devote to each source. So you could imagine that you're restricting the sum of the betas to be 1. You could have imagined that if I devote a little bit of attention, it becomes much easier to absorb the rest of the information in the article, which might be something like the sum of the square roots of the betas is constant.
Yeah, that's certainly possible. We could have written down different sort of mappings from attention allocation into the precisions of the signals. So the way that we chose, I think it's actually best motivated by considering this discrete time example, right? So if you do literally want to think about this as, say, different testing centers, and you have some batch of tests, right? Then if I were to allocate N1 tests to testing center 1, and if we want to think about that as a Gaussian signal, right? Then I think in that discrete time model, the most natural way of modeling that signal that you get is just a signal about theta 1, where the error variance is 1 divided by n. Or if you want to think about this as different experiments too, right? Like different lab experiments, you have some total number of subjects, then 1 divided by the total number of subjects is going to be your variance. So I think if you find that that motivation reasonable in the discrete time setting, then this is just the continuous time analog.
So, but like, do your results rely on that being held constant, or can have other functions of the betas held constant?
So I think the results do, yeah. If we were to change this this formulation, that would also change the results.
So Annie, at this stage, can I also interrupt you here? So I have a bit of trouble in the mapping between the continuous time and the discrete time, because as opposed to the variance, why is it that in the continuous time, how much allocation do you attribute affects the drift, whereas in the discrete time one, it doesn't? I would expect that the less attention you allocate also in discrete time, the more bias. So I was expecting a beta multiplying the theta I in the discrete time analog.
Yeah, good. Okay, so if you look at this expression for the diffusion process, right? If you divide through by beta IT, then it looks a lot like this one. Right, so then we'll have the drift just be theta I. Okay, you have to pull this outside of, if you pull this outside of the error, then that's going to be the square root.
I see. So no, I understand that. But then the more general point is how it comes that when you say allocate no attention at all, you still get an unbiased signal. It may be very imprecise, but you still get an unbiased signal. So is there an intuition for you adopting this modelization? I would expect that, if you don't allocate any attention at all, then this relies on your prior being correct, basically, right?
So if you don't, I'm not sure I'm understanding the question. So I think if you don't allocate any attention at all, then the increment is completely uninformative.
It is an informative in the Bayesian sense, in the sense that you have a posterior that has zero precision, right? But the mean is still zero in your normal, in your discrete time analog.
Right, so it's just pure noise in that case.
Okay, but it's zero mean noise. So this means that you have a prior that is correct. And, by allocating information, the only thing you do is improving the precision of your posterior.
So I'm not exactly sure I'm understanding this question here because.
Okay, don't worry. I don't want to hold you up. Carry on. We can discuss that later.
Hector, yeah, sorry. Shall we postpone the questions to the end? Yeah.
All right. But okay, so I guess as long as we do agree that if you don't allocate any attention, then the increment is not going to be informative in the Bayesian learning sense, right? As you say, but then we do have this Bayesian decision maker. So you do have to allocate some attention to be able to learn from that source. Okay, and then just reiterating Nicole's nice point, right? So we do have this specific formulation of how attention impacts the informativeness, which we think of as being motivated by this discrete time setting. But if you were to change that, then potentially the results would also change. Okay, great. All right, so the decision maker gets to observe the complete path of each of these processes. Right, so at any given moment in time, the history is going to look like this. And the information acquisition strategy then is going to be a map from any such history into a choice of how to allocate attention right now. Okay. In addition to that information acquisition strategy, the decision maker is also going to choose a stopping rule. So at every given history, he's going to decide whether to continue sampling and acquiring information or whether to stop and just make a decision right now. Right, so whenever he does stop, he takes an action, right? He engages in a decision problem where he takes an action A and receives a payoff which depends on the action that he chose, this unidimensional payoff relevant state omega, which remember is a linear combination of the attributes, and finally on the time of stopping. Okay, and we essentially don't impose any constraints on what this decision problem looks like. Okay, besides that, it must depend only on this payoff relevant state omega. We do impose a very weak restriction, which says that holding fixed your belief at the time of stopping, you prefer to stop earlier rather than later. So this is going to accommodate most models of time costs. All right, just a couple of comments on the model and its relationship to the literature. So first, this is not a multi-armed bandit problem, although superficially it might look like that. The main difference is that in our model, we have the separation between the choices that you make, which determine the information that you receive, and then also this action that you take at the very end, right? So we don't have the standard exploration-exploitation trade-off that's central to MAB problems. Okay, so that positions our paper as a paper on pure dynamic learning, which is related to this recent literature. Relative to these papers, our paper is going to allow for many different signals with flexible correlation. Right. Finally, there's also been a recent literature on rational inattention and flexible information acquisition, usually modeling informational costs as using something like entropy. Right. The main difference between that way of modeling costs and ours is that something like entropy is prior dependent, meaning that the cost of your information is going to depend on your current belief. In contrast, our informational cost is prior independent, which we think of as being a better model for settings in which the cost of information is physical. Right? So if you think about the COVID case, the mayor might just have some limited number of physical tests that can be allocated. It's not that, like, if the mayor knows more about the COVID incidence rate, he's going to find it cheaper to access more tests. All right. So
Annie, there's a question in the chat.
Okay.
I wonder, how does the result change if the decision maker has to take actions every period? For example, in the COVID setting, one would expect the government to take decisions continuously.
Yeah, that's a great question. So we do have an extension in the paper to multiple decisions over time. So things get a little bit more complicated to pose technically with continuous choices of actions. So our extension is to a discrete number, like a finite number. You can also, I think, extend this to just every discrete period, say, take an action.
So if you do that, does it become a multi-arm bandit problem?
It still doesn't, as long as those actions are separate from the information acquisition choices. Right, yeah, great. And hopefully when I get to the intuition for the proof, you can also sort of see the sense in which it's going to be okay to also add actions, multiple actions along the way. All right, great. So let me now tell you about our characterization of the optimal information acquisition strategy in this problem. I'll show you two results. First, a result for the case of just two attributes. Here we're able to obtain a slightly sharper result. Then I'll show you how things generalize for an arbitrary finite number of attributes. All right, so for two attributes, the problem is pretty simple. We have just two unknowns, theta1 and theta2, again, jointly normal. The payoff relevant state is some omega, which is a linear combination of the two attributes. And we're going to adopt the convention that the payoff weights alpha are strictly positive. So that's actually without loss, because if an attribute were negative, we could simply redefine it to be its own. If a payoff weight was negative, we could redefine the associated attribute as its own negative, and then that would return a positive payoff weight. Okay, so that's without loss, but let's just remember that alphas are going to be positive. All right, so for a characterization to hold, we're going to need an assumption on the prior belief of the agent over these attributes. So let me now tell you what that condition is. So for each of these attributes, theta I, define cov I to be the covariance between theta I and omega, the payoff relevant state. Right. Here's the expression for that. The condition that we need is that the sum of the two covariances is weakly positive. Right, so here I've just written out the expression for that sum. And if we just stare at it, well, sigma 1,1 and sigma 2,2 are both variances, so they have to be positive. And in addition, these payoff weights are by convention positive. So the only way that this expression could be negative is if this covariance was rather negative relative to the sizes of the variances. And that's the case we're ruling out. All right, so hopefully that offers some interpretation into the condition, but let me offer you just a few more, even more interpretable sufficient conditions for that. So one sufficient condition is for the payoff weights to be the same. That includes, for example, the case in which omega is the sum of the attributes. All right, another sufficient condition is for the attributes to be not negatively correlated. In fact, they're positively correlated. Right, so that'll also do it. And a final sufficient condition is for the decision maker's initial uncertainty about the two attributes to be the same. Right, so then under any of these sufficient conditions, or under this weaker condition up here about the sum of the covariances, we're going to be able to characterize this optimal attention allocation strategy.
Hey, just to clarify, so the condition you have there, that interacts with the convention that alpha is positive, or does it not? If I have alpha negative and then I redefine the state here, then I'm not sure I can see it directly from the condition, but some of the sigmas change sign as well. And
no, so that's a good point. So the condition is stated on this version of the model. So if you had a different version of the model, you would first have to transform it like this and then verify that this condition is satisfied in this transformed version of the model.
Yeah, okay. Mm-hmm.
All right. So great. So without loss, let's suppose that theta 1 is the attribute with the weakly higher initial covariance with the payoff relevant state. And let's define T1 as follows. Right. Then the optimal attention allocation strategy has 2 stages. So in the first stage, the decision maker is going to allocate all attention to attribute 1. And in the second stage, right, so first stage lasts until this time T1 given here. Right. In the second stage, which is all times afterwards, the decision maker is going to allocate attention in a constant fraction, which is proportional to the payoff weights alpha 1 and alpha 2. Right, so let me just make a couple of comments or observations, right, from this result. So what's really interesting here is what's not on the slide. So one thing that's not on the slide is the realizations of the diffusion processes. Right, so we see that this attention strategy is actually history independent, meaning the decision maker actually knows at time 0 exactly how he wants to acquire information going forward. Right. Another thing that's not on this slide is the payoff function, right, or anything about, let's say, the decision maker's time preferences. So what we see then is that as long as that condition on the prior belief is satisfied, this attention allocation strategy is optimal across decision problems. Right, and those are both going to be properties that are going to be present in the more general version of this result as well. Right, so let me just now illustrate this solution on a couple of simple examples. The simplest possible example is independent attributes. So let's just suppose theta 1 and theta 2 are independent. And let's suppose you have greater initial uncertainty about theta 1 compared to theta 2. Right, let's suppose the payoff relevant state that you want to learn is the sum of the attributes. Right, then applying our characterization, optimally in phase 1, the decision maker is going to begin by allocating all attention towards learning theta 1. At a switch point, okay, given here, the agent's posterior covariance matrix is going to become this identity. And from that point onwards, the decision maker is going to split his attention equally between learning about these 2 attributes, equally because these payoff weights are the same. Right, so now let's make the example a little bit more complicated, keep everything else the same except this correlation, right? So previously they were independent. Let's now introduce some correlation. So then again, in phase 1, the decision maker is going to put all attention towards learning about theta 1. Again, there's going to be a time point at which the decision maker's uncertainty about the 2 attributes becomes the same. Again, from that point onwards, the decision maker is going to split attention equally between learning about the 2 attributes. What's changed is that this switch point has gone later. And moreover, the uncertainty, the variances at the switch point are lower. Right, so the reason for that is because this correlation introduces a sort of learning spillover effect, where although in phase 1, the decision maker is only acquiring information about theta 1, that information is also informing the decision maker about theta 2. Right, so his uncertainty about theta 1 is going down, but his uncertainty about theta 2 is also going down. So now it's going to take longer for the decision maker's uncertainty about theta 1 to catch up with his uncertainty about theta 2. So that results in this later switch point. All right, so that's the case of 2 attributes. For 3 attributes, we're going to obtain a very similar result. And again, we're going to need a condition on the prior belief. And here we have 3 different sufficient conditions. Let me emphasize that we don't need all 3 of them to be satisfied, just one. In fact, some of these are mutually exclusive. So the first condition, called perpetual substitutes here, says that the prior precision matrix, that's the inverse of the prior covariance matrix, has negative off-diagonal entries. And what that gives us is that the partial correlation between any pair of attributes, controlling for all of the other attributes, is positive. Okay, don't get too confused about this sign change. That just is the way it happens to be. All right. And we call it perpetual substitutes for a good reason, which is that this condition turns out to be necessary and sufficient for any pair of sources to provide substitutable information, not just in the prior, but actually along the whole path of learning. So let me not go into too much detail here, but if you're interested, we would be delighted if you would take a look at the paper to learn more about that relationship. All right, the second condition says that the prior covariance matrix has negative off-diagonal entries, which gives us that the prior covariances between different attributes is negative. However, the covariance between each attribute and the payoff relevant state, which remember is a positive linear combination of the attributes, that covariance is positive. So the second condition is going to put a bound on how negative these covariances can be between the different pairs. So just roughly speaking, what it gives us is that prior covariances between attributes are mildly negative. And the final condition is more of a technical condition. It says that this prior precision matrix is diagonally dominant. And I'm just reminding you here of that definition. So this final condition roughly says that the covariance matrix, the prior covariance matrix, can't be too far away from the identity. All right, so then under any of these three conditions, we're going to be able to again obtain a characterization of the optimal attention allocation strategy. Right, so there's going to exist a sequence of times and a sequence of nested sets such that an optimal information acquisition strategy is described by a deterministic path of attention allocations, where at each stage, and by stage I mean the time in between any two time steps, there's going to be a constant mixture, okay, which is supported on the sources in the associated set. So initially the decision maker begins by learning from maybe just one source, you put all your attention there, eventually you add in some sources, you change to a new mixture over the set of sources, but it's a constant mixture until you hit the next time step. Then you add in more sources, switch to a new mixture, so on and so forth. And as in the case of two attributes, in the final stage, attention is going to be proportional to the weight vector alpha, right? Again, defining this linear combination. All right. Here, I'm not giving you the closed form expressions for the time steps, the nested sets, and the mixtures as I did in the two attribute case, but in fact, the full path of attention allocations can be computed from these primitives, alpha, the weight vector, and sigma, the prior covariance matrix, just as in the two attribute case. And we have an algorithm in the paper explaining how to do that. All right, and again, just like in the two attribute case, we see that the optimal attention allocation strategy is history independent, right? You can map out this whole path from time t is equal to 0. Again, we see that it's robust across decision problems. The payoff function doesn't play a role. And we also see that the solution is independent of the stopping rule, right? And that actually turns out to be extremely convenient because it means that you don't have to solve for the stopping rule and the information acquisition strategy jointly in this problem. You can actually take information acquisition as given exogenously by this solution given here. And then you can solve for the stopping rule in that simpler problem. And that's a feature we're actually going to take advantage of in one of the applications. All right, so now let me just spend some time giving you an explanation for why the characterization ends up looking like this and having some of the properties just described. All right, so I think it's easiest to begin by thinking about a static version of this problem. So let's go back to the COVID case, right? There's 3 different testing centers, 3 different neighborhoods associated with the testing centers. Let's let theta 1, theta 2, theta 3, the attributes, be the incidence rates of COVID in each of the associated neighborhoods. Right, omega is going to be the aggregate COVID incidence rate in the city, so that's going to be some weighted average of these primitive attributes. Okay, you're the mayor. You have, let's say, a one-time budget of T total tests to allocate across these testing centers. Your goal is just to maximize to minimize your uncertainty about omega, right? And that's going to be your goal because in our Gaussian setting, posterior variance is a sufficient statistic for your uncertainty. And minimizing uncertainty about omega is going to be Blackwell best, right? It doesn't matter what decision problem you're facing, which depends on omega. What you want to do in any case is to minimize your uncertainty about omega. All right. So this static problem is very straightforward. Posterior variance can be written as a function just of the counts of the number of tests allocated to each testing center. Okay, in particular, the signal realizations don't matter. That follows from our Gaussian environment. So what you want to do then is simply identify the Q1, Q2, Q3 that minimizes your posterior variance about omega, subject to those counts, okay, being weakly less than T, your total budget. And let's just define Q star of T to be that optimal allocation of a one-time budget of T total tests. All right, so that's pretty straightforward, right? That's just for the static problem. What makes a dynamic problem harder? Well, suppose it turns out that with 100 total tests, the optimal way of allocating that were to allocate 100 total tests to testing center 1, 0 to 2, and 0 to 3. Right. By the way, I've stated this as a static problem, but just note also that there's a close relationship between the static problem and the dynamic problem with a known end date. So let me actually just go back and clarify this point, right? So if in our main model, right, you know for sure you're going to stop at time t, then again, the solution is pretty straightforward. What you want to do is just allocate information dynamically in any way that's going to accumulate to Q star of t at time t. Right, the order doesn't matter. Okay, great. So then going back to this 100 total tests, whether you want to think about it as a one-time budget of 100 total tests or as a decision problem with a known end date of time 100, those are going to be in a sense equivalent. Right. So suppose this is your solution here, right? 100, 0, 0. And suppose that the solution to the problem of how to allocate 101 total tests looks like this. You want to allocate 1 to testing center 1, 50 to 2, and 50 to 3. So what you immediately see is that these two solutions are, in a sense, in conflict with one another, because it's not going to be possible to achieve both under the same sampling strategy. Right? Conditional on achieving this solution at time 100, you would have to take back tests that you've already allocated in order to achieve this optimal solution for 101. So what that means is that this decision maker facing a dynamic problem has to make a trade-off, right? He has to decide, do I value more the possibility of making a more accurate decision at time 100? Or do I value more making a more accurate decision at time 101? And in general, your trade-off between those two periods is going to depend on all of those things that we just said didn't matter, right? It's going to depend on your decision problem, your stopping rule, so forth.
I need 28 minutes.
Okay, thank you. All right. So the key idea here, though, is that if we don't have a problem like this, where you have to take back information already given, if instead Q star of t, these optimal static allocations of t unit of time, if that's actually increasing in each of its coordinates, then it is going to be possible to, in fact, string together all of these optimal static solutions using a single sampling strategy. And in that case, we're going to call that strategy uniformly optimal. Right? Uniformly optimal in the sense that it's not just minimizing posterior variance at some point in time, it's actually minimizing posterior variance at every moment. Right? And intuitively, we might think that such a strategy would be best across different intertemporal decision problems, because you don't have to make these trade-offs across periods. That in fact requires argument, but it does turn out to be true. Right? So if a uniformly optimal strategy exists, it's best across decision problems. All right, so then this changes the question to when is it the case that Q star of t is in fact weakly increasing in each of its coordinates? And are different sufficient conditions all guarantee that monotonicity property? Right, so just a sort of quick word on that, right? It turns out that there is an analogy between that question of when these T-optimal attention vectors are increasing in T, with a classic problem from consumer demand theory. So consider a consumer who's choosing consumption over K different goods. Q of K is your quantity of consumption for the corresponding good K. Right. Fixing a price vector P and a total wealth level W, let D of PW denote the consumer's demand subject to this budget constraint. Right? Your total expenditures can't exceed your total wealth. Then sort of an old concept from intermediate micro is that demand is normal if each coordinate of your demand function is increasing in your income. So as you get wealthier, you're going to demand more of each of these goods. Right. Then if we let your utility function be negative of the posterior variance, if we define the price vector to be this vector of all ones, and your wealth level to be T, your attention budget, then normality of demand is equivalent to this monotonicity property of these T-optimal attention allocations. And indeed, one of our sufficient conditions, perpetual complementarity, is actually directly related to a sufficient condition for normality of demand from that literature. The other two sufficient conditions we have exploit specific properties of our utility function here. Okay, and potentially they generalize beyond that, but that's not something we've looked at yet. All right, and since I'm running a little bit lower on time, let me just skip this last part. But so the final comment is that when a uniformly optimal strategy exists, then the attention allocations are simply the time derivatives of these T-optimal vectors. Right, at every moment of time, you can just ask, what is the mixture that's going to maximally reduce my uncertainty about omega? You don't have to worry about the future. So in a sense, one of the implications of our characterization is that greedy optimization is optimal under the given condition on the prior. And then from that, we can derive this nested set property of the characterization. But let me just skip that for now. All right. So for us, just various abstract properties of the solution were interesting and for us surprising. But even if you don't care about that on its own, we hope that the simplicity of this characterization will make it amenable towards applications. And in our paper, we use this characterization to derive new results in 3 different applications, where we use the characterization to tractably introduce correlation in settings that have previously only been studied under strong assumptions of independence. And we use the characterization to derive new results about other economic behaviors. So I just wanted to spend the rest of the time we have together telling you about those applications. All right, so the first application is to binary choice. So there's a literature here considering the problem of a consumer who has a choice between 2 goods, where the consumer doesn't know the payoffs of those goods, right, but can receive information about those payoffs or can learn about those payoffs over time. So recently, Freudenberg, Strack, and Syrgkanis proposed what they called the uncertain drift diffusion model, where the payoffs of the 2 goods are modeled as being jointly normal with a specific kind of prior covariance matrix. Right, so this prior covariance matrix has that the payoffs are independent from one another. And moreover, the consumer's initial uncertainty about the 2 payoffs is the same. Right. Then they assume that the agent can continuously divide a unit of attention across 2 Brownian processes whose drifts are these unknown payoffs, V1 and V2. And the agent chooses a stopping time to maximize the following objective criterion. So whenever you stop, you're going to choose the good with the higher expectation at that stopping time. And you have a linear weighting cost. So in this problem, the payoff difference V1 minus V2 is a sufficient statistic for your decision. And that means that we can actually nest that problem in our framework. So simply define theta 1 to be V1 and theta 2 to be negative V2. Then the payoff relevant state omega is simply the sum of these attributes, which is also equivalent to the difference in the payoffs. Okay, so that's what you're trying to learn about. All right, and then noting, by the way, that here we have equal payoff weights, And remembering that equal payoff weights was one of the sufficient conditions for our characterization to hold, we immediately see that we can actually apply our characterization in this setting, not just for this special prior covariance matrix considered in this paper, but in fact for any prior covariance matrix. And we see that as not just a technical generalization, but one that allows for incorporation of important realism in these settings, because correlation and asymmetry are both rather typical properties of choice environments. Right? If you're choosing between two stocks, their values are going to be correlated by global economic shocks. If I'm choosing between a next computer, is it going to be a PC or a Mac? I've used Macs for the last decade, so my uncertainty about that value to me is fairly small. My uncertainty about the value of a PC is rather large, so that would correspond to a case where these initial uncertainties are rather different. All right, so we're going to be able to generalize a couple of different results from this paper. The first one is a result about optimal endogenous allocation of attention. So they show that starting from this prior covariance matrix, the agent is going to optimally divide attention equally between learning about these two payoffs at every moment of time. And then this first generalization is just immediate, right? Because already observing that we can apply our characterization, we immediately know that from any prior covariance matrix, the attention allocation strategy is going to take the following form. Right? So there's going to be two stages. In the first stage, the decision maker is going to allocate all attention towards learning about the payoff, which is less known initially. And after a certain point in time, whose expression is given here, the agent is going to optimally allocate attention equally across the attributes. So this previous result is in a sense robust or general because even allowing for correlation and asymmetry, eventually the agent is going to allocate attention in that fashion. But the role of asymmetry and correlation is to introduce this first stage. And the length of that first stage we can show is increasing both in the asymmetry between these initial uncertainties, as well as in the correlation between the payoffs. All right, so this was just sort of an immediate implication of our characterization. Okay. The second generalization is going to take more work, but also be more interesting. So the main result in this paper regards the relationship between decision times and choice accuracy. So what we can ask is, conditional on the decision maker choosing to stop at time t, what is the probability that the decision maker is going to choose the higher value good, right? The truly better of the two goods. And let's define that to be this P of t. So how P of t evolves in t is not obvious because there's two competing forces. Okay. On the one hand, if you stop later, well, mechanically you've received more information. So that's a force that's going to lead your later decisions to be more accurate. Okay. On the other hand, these decision times are endogenous, right? So conditional on choosing to stop earlier, that's probably because you've received information that's rather conclusive, right? Information that's telling you that one of these goods is much better than the other. So their proposition 3 says that, in fact, the second force dominates. This function P of t is weakly decreasing over time, meaning earlier decisions are more accurate, right? So if you would observe this decision maker making many decisions, then the times at which they were stopping later are going to be correlated with poorer choices. Right. Now, again, because they maintain this assumption on the prior covariance matrix throughout, this result was proved under this prior covariance matrix. So we might wonder whether that result depends in a special way on this assumption of independence or potentially on this assumption of symmetry in these initial uncertainties. And what we're able to show is that it doesn't. So this result that earlier decision times are more accurate generalizes, in fact, to any prior covariance matrix. All right, so I don't have time, unfortunately, to tell you too much about why that ends up being true. But one thing I at least wanted to do is give you a sense of how our characterization was useful in showing that.
I mean, just to clarify, so the way this is stated here, is any sigma allowed, or is it any sigma where the correlation isn't too negative?
Great, thanks for the question. Yeah, this is for any sigma. And that's because this special case of a binary choice problem corresponds, let me just show this slide again, right? It corresponds to equal payoff weights. Alpha 1 equal to alpha 2. And remember that was,
and for that case, you don't have any restriction from your condition.
That's right. The payoff weights being the same is a sufficient condition for the two attribute case. Yeah. So that does end up being convenient here.
Yeah. Okay.
So we don't need any further assumptions on the covariance matrix. Yeah. But thanks for pointing that out.
I mean, maybe more generally, if you had let's say you would care more about one decision than the other, you have different payoffs for them, and then you have a different weight on the two attributes. Do you have a sense that the result depends on this uniformly optimal property of the information acquisition, or because I mean this is kind of a general question you could ask there as well, right? So why do you restrict to this symmetric case?
So if I understand the question correctly, we do actually have a generalization in the appendix, possibly in the online appendix, of this result for different payoff weights too, or relatedly also for different learning speeds. But in that case, then your question does bind. So we will need further assumptions on the correlation.
So there are cases where this is not true, that result, in asymmetric payoff weights, and for some.
There are cases at least where we can't apply our characterization. So it's not that we have a counterexample, but at least
it's not known whether the converse. Okay. Mm-hmm.
Because right, so our strategy involves use of our characterization, right?
Okay.
And okay, yeah, great. Yeah. Okay, yeah. So our strategy involves use of our characterization. Let me just quickly tell you about how that ends up being useful. So the most immediate way this becomes useful is that it tells us that the optimal attention allocation strategy doesn't depend on the stopping time. So it allows us to make the separation, right? We can suppose that information arrives exogenously in this way. All right. The second thing it tells us is that it actually pins down the evolution of the posterior covariance matrix along this optimal path of learning. And certain properties of that evolution end up being useful for showing that previous result. So one property, the property that actually ends up being useful, is that your asymmetry and uncertainty over the two attributes is actually decreasing in time along the optimal path. Because in phase 1, it's strictly decreasing. And then in phase 2, they just stay together. Okay, can I just get a quick check on time? Do I have?
It's 14 minutes.
Okay, sounds good. So then I roughly have time to basically tell you about the second application.
Thank you.
All right, so the second application is pretty different. In the first application, we're looking at a result that's already been shown out there in the literature, and we're trying to use our characterization to generalize it. In the second application, we're going to write down a new game and use our characterization to solve for equilibrium in that game. All right, so here's the game. We have two news sources. You can think about them as being a liberal news source and a conservative news source. They're going to report on the same unknown state of the world, which you might think of as being the cost of a proposed policy. All right, we're going to assume that it's Gaussian. So we're going to have in mind issues where the partisan implications are not precisely known by the general public. All right, so this is not going to be something like gun control, where we know, everybody knows what the liberal stance is and what the conservative stance is. This is going to be any other issue which is not really covered as much. All right, so for example, new limits on short selling in financial markets, or trade deals with small countries in Southeast Asia. All right, so there is still some benefit to source one when the public thinks that the cost of this policy is large. And we're going to call that benefit B, but that benefit is going to be a random variable from the perspective of the reader capturing this initial uncertainty. All right, so now the two sources are going to bias the reporting about this omega in opposite directions, right? But they're going to get to choose the intensity of their bias and they're going to get to choose the noisiness of their reporting. So specifically, a unit of time spent reading source 1 is going to be equivalent to a realization of this Gaussian signal here, where the mean is omega plus phi 1 times b. Right, phi 1 is this choice of intensity of your bias. And you're definitely going in the direction of b, right, because this is a positive choice and we have a plus here. But you get to decide how much you want to slant in the direction of b. And then zeta 1 is your choice for how, let's say, accurate you want your reporting to be. Okay, source 2, similarly, a unit of time spent on source 2 is going to generate a realization of this signal, where it looks very similar, except note that the sign is different, right? This is a negative here. So source 1 is going in the direction of B, source 2 is going in the opposite direction. Right. Now there's going to be a representative newsreader who faces a decision that depends on omega, and we can be vague about that because, again, remember, this decision problem, the specifics of it aren't going to matter. Right. He has access to the 2 news sources and is going to optimally allocate attention across them over time. So that's going to lead to a path of attention allocations. And then each source's payoff is going to be given by a sum of 2 factors. So the first component is going to be the discounted average attention paid to that source. Right, so R here is the source's discount rate. Beta IT is the amount of attention allocated towards allocated towards source I at time t. Right, so this is capturing something like, it's like an online news source, and the more viewership you get, the more ad revenue you get. Right, the second component of this payoff function is an explicit reward for bias. Right, so you can think of this as reduced form for a larger model in which the sources are somehow beholden to their party that they represent, okay, through donors or their owner or something else like this. So the Liberal Party wants the liberal news source to bias their information in the direction that's useful for the party. But you also don't want them to be infinitely biased because nobody's going to trust that source anymore. So there's going to be some bliss point kappa, which is interior, for this bias intensity. And the source is going to be penalized for how far they are from that bliss point. And in addition, there's going to be this parameter lambda, which moderates the strength of that incentive. So how much pressure are you putting on the source to actually bias to the extent that you want?
One thing one could put in here is the amount the news source can swing the decision of the newsreader.
I see.
And it has a bit of flavor of this, but it's not the same, right?
Yeah, and in our setting, because the newsreader has access to these 2 news sources, which are biased on different sides, the newsreader will eventually be able to learn omega. But actually, this point is going to become important in a moment. So I'll come back to that.
Okay.
All right. Okay, great. So there's this attention part, and there's this direct reward for bias. All right, so how does our characterization become useful? Well, fixing any choices by the sources, right? So this is their bias intensities and the noisiness of their articles. Our characterization is going to allow us to pin down this whole attention path for the reader. Right, then we can take that attention path, plug it into the payoffs that I just showed you, and that's going to be able allow us to derive the payoffs for each of the sources. So then we can use this to solve for equilibrium, right? We can ask, when is it the case that given these choices, you're not going to have a profitable deviation? So that's exactly what we do. And we solve for equilibrium in the setting. So there's a unique pure strategy equilibrium where the bias intensities are given by the closed form expression here. The accuracies are, the noises are given by the expression here. And I don't want you to worry too much about these exact expressions, except to know that they exist. For us, the more interesting result is this corollary here. Right, so this is about the informative of news in equilibrium. So what we can show is that the equilibrium noise level, zeta star, okay, which remember is symmetric in this equilibrium, is increasing in the incentive for bias lambda. Remember, that was the strength of the incentive, as well as in the bias bliss point, the bias intensity bliss point kappa. All right, so that's telling us that incentives for bias, which by the way, explicitly motivates just this choice phi star. Right, so mechanically, larger lambda, larger kappa should lead to a higher choice of bias intensity. And it does, right? So you have higher polarization in equilibrium. But not only is it the case that those higher incentives lead to higher polarization, but they also lead to a decrease in the quality of reporting via a choice of higher noise levels here. Okay, and notice that these are separate choices, right? So you might actually think, right, that if these sources are providing more polarized information, which in a sense already means that they're providing worse information, they might want to compensate for that by at least providing more accurate reporting. And it turns out that that's not the case. These higher incentives lead to worse information in two separate ways. You have this higher polarization and you have less accurate reporting. Right? And I'll give you an intuition for why that turns out to be true in a moment. The second part of this corollary says that the equilibrium noise level is decreasing in the discount rate R, meaning that patient news sources are also providing lower quality news. Right, so I'm going to explain both of these together now. So for simplicity, let's just suppose that the bias intensities are the same. Right, so whatever omega is, one source is going some distance to the is augmenting omega by some amount, and the other is sort of reducing omega by the same amount. Okay, we can now apply our characterization and show that there are two stages of information acquisition. In the first stage, the source with the smaller noise zeta I, so namely the source that's providing the more precise information, is going to receive all viewership. In the second stage, sources are going to both receive a fraction of viewership, and that fraction is going to be proportional to their noise levels. So the noisier your information is, the more viewership you receive, right? And that's roughly because conditional on you having something to tell the readers, right, that they have to come to you for, the slower you provide that information, right, the worse your information is, the longer they have to spend on your site to actually extract the same quality of information. All right, so then this characterization tells us that firms face a trade-off between optimizing for long-run viewership, where there is this exploitation incentive, right, and you actually want to provide higher noise, versus competing to be chosen in the short run, where this force pushes you to want to provide more precise information, right? So let me just say that one more time. So there's this trade-off between the long run and the short run. When you're thinking about the long run, you prefer to provide worse information in the sense of noisier information. When you're thinking about the short run, you prefer to provide less noisy information. So how large equilibrium noise turns out to be is going to depend on how you sort of weigh these two concerns. And parameter values that emphasize the long run are then going to lead to higher equilibrium noise levels. So what emphasizes the long run? Well, the most obvious one is patience, right? The more patient these news sources are, the more this discounted average attention the more weight that places on your long run payoffs. And hence, the higher this exploitation incentive, and hence the higher equilibrium noise turns out to be. Okay, less obvious, but what also turns out to be the case, is that higher incentives for bias in this environment also emphasize the role of the long run. Right, so why is that? So if we think about two news sources which are both very polarized, right? In a sense, these sources actually live in a kind of symbiosis. The more extreme the right gets, the more important it becomes to go to the left to actually debias your information, right? So this goes back to the earlier conversation with Konrad. Eventually you can learn omega because you have access to these sources that are biased on opposite directions. But the more polarized they are, the more complementary these two sources are. And then when the two sources are complementary, you actually sort of derive more value from mixing over them. And remember, the second stage is the mixing stage. The first stage is just all attention towards one source. So you can actually show that when these incentives for bias are higher, you actually switch from stage 1 to stage 2 earlier. So that's another force pushing the long run to become sort of more important, which then leads to higher equilibrium noise. Right, one thing to just emphasize here is that the comparative static we get really does rely on the rule of dynamics in this problem. And the only reason we're able to solve for that pretty straightforwardly is by having this characterization, which we can simply plug in. Okay, great. So we have those 2 applications in the paper. We actually also have a third, which I won't.
1 minute more, yeah.
Oh, 1 minute, perfect. Okay. So we have a third application, which I won't go into detail towards today. But there's this recent paper also by Gostner et al., which looks at this question of what happens if the agent doesn't have full control over their information, but instead you can actually, say, distract this decision maker for an initial period. And how does that initial distraction lead to differences in their subsequent information gatherings? So we're able to pose a very similar question in our framework. So the 2 frameworks turn out to be non-nested, so it's not a generalization of their result. But we're able to derive complementary results to what they find. And the sense in which we're able to go beyond is by looking at correlation also and how that affects these long run effects. All right, so yeah, so that's actually all I had to say. So what we did in this paper is we studied optimal dynamic allocation of attention across multiple correlated informational sources. And it turns out that under a weak condition on the prior belief, the solution has a rather simple structure. It's history independent, and it's moreover robust across decision problems. And we found that it was useful for us in thinking about certain applications, again, whether it's sort of generalizing an existing result or sort of looking at complementary results or trying to derive new results in a new situation. Yeah, I guess we hope that it might be useful also to other people in applications that you might all be looking at too. Okay, thank you for your time.
Thank you, Annie. Thanks a lot for the very interesting talk. We'll stop recording at this stage, and we'll have our panelists to step in and ask any questions they may have to begin with.
We don't stop recording yet.
Yeah, I'm stopping it. Yeah.
We are not.
Hmm?
No.
We are not yet stopping at
Not yet. Okay.
No controversial.
We want to have our panelists on record. Go on then.
Unless there are controversial
does this a lot.
questions,
Okay.
Annie, thanks for that talk. It was very enlightening. And I was focused mostly on the evolution of the attention spans on the different information sources and the sensitivity of those to different assumptions and the implications in different applications. But I don't know if you covered this and I just missed it, but there's also this like, when do I take the decision elements?
That's right, yeah. Yeah, so we basically don't look at that in the paper at all. So the only place where we even get close is that application that I mentioned about binary choice. And even there, we don't solve for the stop and roll. It turns out to be pretty difficult. So we were able to say something about it, but.
So you don't have any general sort of like comparative statics about that or something?
Outside of that setting, no, yeah. But we hope that this, the result here, which again is just about information acquisition strategy, we at least hope that this could be useful in that problem, right? If that's something you were more interested in.
Yeah, I guess it seems like it should play a little bit into even in the last application that you presented, the strategies of the news sources, because I guess once I take a decision, I'm going to stop reading the news in this world.
That's right, yeah. So you're pointing out that we have this assumption that you're sort of acquiring information infinitely. Yeah, which was just to reduce one of the moving parts. Mm-hmm. Yeah, I mean, so you can justify that as something like low informational costs, but you're absolutely right that if you wanted to take that application more seriously, you might also want to include the stop in time.
Is that something that's very hard to
yes.
characterize in that application?
Yeah, no, it's hard to characterize even in the binary choice application, which is but in a sense a simpler case.
I see.
So yeah, and so again, that's just not the focus of this paper. Like we were interested in information acquisition, but yeah, could certainly be an interesting.
The presentation really makes clear that the framework is quite useful for speaking to these applications, right? And I think it's nice that a large chunk of the talk is about the applications, because they really illustrate that it's quite useful to embed this in an applied framework. I was just I think it would be nice to go further in the last application. I think it's a really important application, and this question about whether I can swing the decision of an agent is, I think that's one of the key elements that biased media might want to do, right? And I don't know. I mean, maybe you cannot characterize the stopping time, but if you can say, analogous to the first application, something about the mistakes that people make when they decide in this application, then maybe you can also say something about in what direction is their decision biased, depending on what the news sources feed them. I don't know whether this is feasible technically, but I think even without the characterization, there may be something to be done. And I think then the application becomes almost like a full-fledged paper, because I think that's something that many people will find interesting.
Right. Yeah, no, at some point, right, with economics papers, each paper becomes like.
Yeah, no, you should do everything in one, of course. Yeah.
No, but that's a really interesting idea. We hadn't thought about that. So, right, so you're suggesting that in some sense we could like combine the questions of the first two applications and ask. So this is also incorporating Nicole's suggestion, right? So if there were a stopping time in that news consumption model, and then if we were to look at the accuracy of your decision conditional on stopping, maybe not the accuracy, but the slant. Which direction are you making an error in? Yeah, that's super interesting. We hadn't thought about that at all.
I guess in the first example, you always look at the symmetric case, and then the question of, no, because there's no biases in the news sources in the first case, right? That's the difference in the first application. So now
in the two payoffs, that's right. Yeah, so there's no biases there.
Yeah. Okay.
No, but we could look at what happens if you redefined those drifts to be biased.
Yeah.
And then, it really would be a similar question. Yeah, that's definitely food for thought.
I have a couple of smaller comments, but I don't want to dominate the discussion if the other people want to say something first. So maybe, I mean, one.
Corrad, it's your job, huh?
Okay. so just something very small in the second theorem, when you have k greater than 2, you don't need to bring it up. I was just thinking, if for generic covariance matrices, the difference between the sets at each step should be just one news source. Is that correct? Or
yeah. So exactly.
And in that case, is there a simple way to? I mean, you mentioned an algorithm for figuring out the order in which you use them. Does that become quite easy to understand and simple if you know that you're in this generic case that you always add just one additional news source, or is it complicated?
I'm not sure that simplifies it a ton. Yeah, so let me just point out what Konrad had observed, I guess, for everyone else. So like the only reason you would add two sources in together is if like they happen to have exactly the same marginal values. So that might be sort of a knife edge case. Sort of generically, it would be the next maximizer would be unique. So there are just, I guess, to give some intuition into that that path, right? So what happens is that each time you're focusing on a subset of sources, you can't fully recover alpha, right? Because you need all of the sources to recover alpha. But there is some component of alpha which is learnable given those sources, and analogous to the last stage, right? So in the last stage, you're acquiring information proportional to alpha. That's in a sense like the most efficient way of acquiring information. And then at each of these earlier stages, it's a very similar thing qualitatively. The mixture you're going to choose is going to be the mixture that represents the most efficient way of recovering the learnable part of omega, given these sources. So the algorithm is really just about computing what that efficient representation would be.
There's no simple way of reading off the initial covariance matrix what the order is. So that's what I get from the.
Yeah, don't think so. I mean, maybe we thought about it special cases. Yeah.
And so when your sufficient conditions are violated, then you have this property that if you take the sequence of static decision problems and you ask, okay, well, how would I allocate my first unit? I have an allocation, and if maybe the second unit is allocated in some way, and if I take the result of that, then that's different from allocating both at once, right? Because sometimes what I want to do in the first period is constraining me in the second period. I can't go back so I can see that how you want to solve that if your conditions are violated, when these things are not monotonic, that depends on when you stop. Right? But it doesn't seem to depend directly on what are your payoffs when you stop.
But I guess how your stopping rule would depend on your payoffs, right? In general.
Yeah, but I mean, it could be that someone stops and someone else takes decisions, or I don't know. It would be useful. I mean, maybe if what I conjecture is correct, I think it's an easy thing to point out, because there may be situations where these roles are split, right? You could have one agent who is responsible to say now it's enough, and another to take an action. And I guess maybe these will also interact in reasonable examples. So then your point applies. Okay, let me not.
Well, no, sorry. I just didn't fully understand. So you're saying if there's two agents, maybe one of them is stopping and one of them isn't?
Yeah, or the very simple case that when you stop is exogenous, but there could be variation in different environments. Sometimes you need to stop earlier. Sometimes you have more time, and then you get.
I see.
And then I think, if I understand correctly, the way you acquire information is only affected by the time pattern of the stopping, right? Not what the payoffs are. Is that right? Or
okay, so if there's an exogenous stopping time, then our characterization actually continues to hold.
No. But suppose this is distributed over time, right? Maybe I don't know. In every period, you have a chance that you're forced to stop, right? And so you don't have a specific time at which you know you're going to stop. Right? It can happen at any point in time, but someone else decides for you when that is exogenously. Right?
Okay, but you're interested in exogenous stopping, and then our conditions on the prior not holding. That's the case. Yeah. Got it.
So then I don't need to know what the payoffs are in order to figure out how you would like to acquire.
That's right. I agree with that. That's right.
Okay.
But then whether our characterization would hold or not would depend on, I guess, like the support of this exogenous stopping time.
I see.
And whether it sort of dipped into a region where you have this non-monotonicity.
So you could extend the result potentially by saying, okay, there are certain stopping time distributions. Yeah. I mean, maybe you don't want to do that, but just to kind of explore all options. There are certain stopping time distributions where even if the correlation is very negative, let's say in the simple case, then you would still have this this characterization. Okay.
Yeah. But actually, let me just take that opportunity to clarify also that I know this is not what you were asking, but although we worked with endogenous stopping, assuming the conditions on the prior do hold, if the stopping time is exogenously given, the characterization is exactly the same. Again, just because uniformly optimal strategy is still going to be what you want to use. Cool.
Thank you, Konrad. Are there any other questions, Nicole? Like to step in? No?
I don't have any.
Konrad, you have anything else? Thank you. Thanks both. And to Annie, of course, again. Let's stop recording and then we can have a more informal chat as well. And now we stop it, right?
Yes, now we are not recording.
Okay.
All right.